All right, everyone, welcome to a new video. In this one, we're gonna go over covering spaces, and this is an introductory video. So the idea with this video is to give you the definition, what is a covering space, go over a couple of examples, one of which you already know, and that will be it essentially. And hopefully you will have a feeling for what a covering space is. So in a second video, I will go over results and let's prove some theorems and so on. All right, and well, okay, let me not say anything yet. Let's see. So what is the definition? What's a covering space? So we're gonna start with a topological space X. All right, and we all call this the basis space. And covering space is basically, well, it's another space Y together with a projection from Y to X such that the following property holds. So for every point, little x in X, we should be able to find a path connected neighborhood U containing X. So this tells us already that this X is not arbitrary. This X should be locally path connected. Every point has a path connected neighborhood. And additionally from U, we'll have, U should satisfy the following property, that if I take the preimage of U, this will have a bunch of path components. Let's denote one of them like V. And it will be true that every path component V of the preimage is in fact homeomorphic to U. So what you should picture is that you have the open U, you have all the all the components of the preimage, and all of them look exactly like U. All right. Then there's this observation. As I said, I'm assuming sort of locally path connectedness of the space X. The theory can be, it can be like made a bit more powerful by dropping this assumption, but well, for the examples we will look into, this is not relevant, so it's kind of better to avoid this for technicalities. If you want to see the details, you may want to check Hatcher. And an important remark is that a CW complex, right, it's always locally contractible. So in particular, it's locally path connected. So for CW complexes, this is perfectly fine. And I should say, just for notation, so the space that we start with, we call this the basis space, right? It's the projection. So then P, the projection, we call it the covering map. And the space sitting on top, Y, we call it the covering space, okay? All right, so what is the example that you already know and that we already spent some time with? It's the following. It's R projecting to S1. You just take a real number and you send it to the complex number e to the 2 pi I s. All right. Very good. So why is this a covering map? Why is this a covering space of S1? So take any interval Vn of the form a plus n, comma b plus n. So a and b are fixed, and n, it's an integer number. So here I'm giving you z many vn's. And now the claim is, well, if a and b are a distance at most 1, then the image of all the vn's is an interval, like an actual interval. It's not the whole of S1. I call this u when I denote it this way, which is maybe not very precise, but hopefully intuitively clear. And what I'm claiming is that all these bn's are homeomorphic to u, right? And this is immediate. We did this a few weeks ago. So, okay, so we have basically u, an interval, and it has z many preimages that are homeomorphic to it. And here it is, the picture. So here's this one. Here we have r, and sort of I'm presenting it here on the left-hand side by doing this helix on top of S1 that just wraps around. So like the idea is that I'm unwrapping S1 to R. So here I have some interval U. It has z many preimages, and we see them here as well on the right-hand side. All right. Very good. So a really helpful way of thinking about this picture, alternatively, now that we've seen CW complexes, is as follows. So I present S1 as a CW complex with a single vertex P and a single edge A, right? And let's say I orient this edge in this manner. So this is S1. And out of this EW structure of S1, I can essentially pull it back to R. And what I do, right, so let's say this P is the point 1, then this P0 is the point 0, this is the point 1, this is point 2, this is the point 3. So these are all the preimages of the one vertex, and I turn them into vertices in R. And similarly, this open interval A, it turns into an open, well, into Z many intervals in R. That, I mean, I could denote them by A0, A1, A2, A3, but for simplicity, I just call them R because all of them are identified with R. All right, so this produces for me a CW complex structure in R with infinitely many vertices and edges. And now, well, let's see. Let's see what's happening. So, as we said, as we proved a few weeks back, the fundamental group of S1 based at P, let's say, is basically Z, where basically it's the free group with one generator, and this one generator we can call it just A, right? Because sort of the generator is A itself, then we have another loop which is turning twice, which is A squared. Then we could do the loop that goes with the other orientation, and its homotopy class, we could call it A minus 1, and so on. All right, so here we have the fundamental group, and what you can readily see is that, let's say I fix P0 as my favorite base point in R, what you can see is that basically I can label all the other points in R by how many times, I mean, how do I go from P0 to Pi? So for instance, to go from P0 to P1, I have to do 1A, and to go from P0 to P2, I have to do A squared, and from P0 to P3, I have to do A cubed. So what that tells me is that the fundamental group here on the left-hand side on S1 is now labeling essentially all these vertices, and P0 itself will be labeled by the empty word. Very good. That's pretty much all I wanted to say there. So now we can go to a slightly different example. So for R, what we've seen is that basically we have S1, and we found a covering space of S1 that is simply connected. I mean, in particular, it's R, right? So it's contractible. And what we can do now is instead, well, let's see, what other covering spaces of S1 can we find? And for instance, this is one. This is literally S1 again, but now it's a bit different. So let's see. So what I say is I take S1 and I map it to S1 by multiplying, by doing like the kth power as a complex number. And now the CW structure on this side will correspond to the following thing on the left-hand side. So let's see. So P will have k preimages, right? Like the k roots of the kth roots of unity, and these are labeled as P1, P2, P3, and so on. The interval A will have again also k preimages. That, I mean, I'm just denoting again by A, but maybe I should label them as A1, A2, and so on up to AK. And what we see at the level of fundamental groups is that, well, let's call the generator here like the path that goes, well, I mean, the class of the path that goes around this one in counterclockwise order once, let's call it B, as I denoted here. And what we see is that here B corresponds to doing A k times. So that means that when I look at the induced homomorphism of P, sorry, here there should be like a little star, right? P push forward. We should have it. We see that the push forward here takes the generator B to A to the K. This is visually clear. And what this tells us is that, let me see if I wrote it here. Well, let me make a second remark. And what we see is that, for instance, if I have an element here in pi1 of S1, an element AN, then it will be lifted to a loop if and only if N is divided by K, right? Otherwise, what we'll do is we'll shift N times around this 1 over kth term, and we'll end up somewhere else, right? So that means basically the statement is, it is true that every loop here lifts to a path here, but only sometimes it lifts to a loop as well. Okay, and the statement in this case is that basically the image of pi1 s1 p1, so with generator B, is the subgroup generated by AK. All right. So the image of this by the push forward by the induced homomorphism is the subgroup A to the K, generated by A to the K. All right, and this is sort of the general phenomenon we want to study. So what we'll see is that if we have the pointed path-connected covering spaces of X, which I denote in this way, X tilde P tilde, where P tilde is mapping to some base point P in X, then there's a correspondence between these and the subgroups of the fundamental group at P. All right, and what is the correspondence? Well, to a covering space, you will assign to it the image of its fundamental group. All right, so for instance, to this covering space, to Z to the ZK, we will assign the subgroup generated by AK. And probably this is a comment I should have made already, but observe that a covering space is not just the space itself. I mean, this space is just S1. A covering space really is the space together with the map. Right? It tells us how to project the covering space to the basis space. Very good. And so this is the statement when I've chosen a base point in the covering space. But here, what we can consider is, well, if we consider covering spaces without a choice of base point, then it turns out that then they correspond to subgroups, but up to conjugation. And we saw this already, right? Because we saw that when you change the base point, here you get isomorphic groups, and the isomorphism is given by some conjugation. So we will see this later, and sort of groupoids will play the fundamental groupoid will play a role in proving this. All right, so this is the basic example that you probably already knew, right? This is probably a good chance for you to go back to our notes about the fundamental group of S1 and review all the theory, because in the next video we will we will explain how the construction we did to compute pi1 of S1 in fact can be applied in general to compute the pi1 of other spaces by looking at the covering space. At covering spaces. All right, so let's look at a second example that hopefully will give you a bit more of a feeling for this. Okay, so let's consider as our base space, the following space. I call it X. It's a graph, right? So a one-dimensional CW complex, and it's given by this picture. So it has one vertex and it has two edges. That the vertex I label by P, and the edges I label by A and B. Let me see. So as we know, right, so this is a wedge of S1s, and by Van Kampen, we can compute readily its fundamental group, and it will be the free group with two generators, which we label A and B, right? So the first thing we can do, sort of mimicking what we just did for S1, is we can unwrap along this A, right? So before we had one S1 and we unwrapped it, and now what I can do is basically leave B untouched and unwrap along A. And in this manner, I'm going to define a covering space that I'm going to call x1 tilde. This is, I mean, I'm going to define others later, so I just label this x1 tilde to keep track of the different ones. So okay, I just unwrap A. So what that does for me is it creates infinitely many edges that I label A0, A1, A2, A3, and this will map to A later. It creates infinitely many vertices, P0, P1, P2, P3, P4, and so on. And now this is the important thing, right? So this, when I unwrap along A, each preimage of Pi should have a neighborhood that is isomorphic to the neighborhood of P. And that tells me that a neighborhood of Pi must look like this. It must have four edges. One, two of them, this and this, are outgoing with this or in these orientations, and two of them are ingoing, right? So that tells me that as I unwrap A, so I get infinitely many AIs, I must also get infinitely many BIs. And because these I'm not unwrapping, they are just sort of copies of B shifted to start at Pi. Okay, and these are denoted by V0, V1, V2, and so on. All right. So okay, first exercise that you should do is the following. It's that x1 tilde is in fact the homotopy equivalent to an infinite wedge, so z many s1s. All right. And this is not very hard, so it's clear that you can define a map from x1 tilde to the wedge by collapsing this whole R line. And the homotopy inverse is sort of given by taking the sort of, let's say, the ith S1 here and mapping it to a loop that does like this. It goes all the way here, it does the ith, like it does bi, and then it comes back. All right, so you should try to prove that homotopy inverse to the obvious projection here. All right, so taking this, looking at this homotopy equivalence, then we know that the fundamental group of x1 tilde, let's say based at p0, but it doesn't matter, of course, because this is path connected. This fundamental group is isomorphic to the free group on z generators, right? Because we have z many s1s. And what is a good way of labeling these generators explicitly? So let's see. So here we have, let's say we're at P0, right? We said. So a loop is, one loop, for instance, a generator is B0. Then what other loops can I define? Well, I can go through A0, I can do B1, and I can come back. So this is this generator. And similarly, I can, let's say, go to Pn by doing this. So A0 to an minus 1, then I do bn, and then I return. So this defines my z generators of the group. And now the question is, what is the induced homomorphism to the pi1 of x, right? To the pi1 of our original space. And of course, the bi is mapped to b, and the ai is mapped to a. So then the image is this, is b, and then all the elements of, like, all the conjugations of b by a to the n. All right, so this is again, hopefully, if you still have some doubts about how induced homomorphisms work, hopefully this will become much more clear by looking at this covering space theory, because here, as you see, it's kind of extremely explicit. And a good remark to be made at this point is that, okay, again, we see this. So out of a covering space, we define a subgroup. And what we see is a funny thing, which is that this subgroup, well, what is it? It's basically the free group with z generators, and we've been able to put it inside the free group with 2 generators, right? Which, I don't know, maybe if you've never seen this group theory fact before, maybe this is surprising, but this is how you can put it in. All right, and maybe, well, let's maybe move on to the next example. So here I unwrapped A in like completely, let's say, but we could have unwrapped A partially, as we did for the case of S1, and I can basically unwrap it k times, and this yields the following covering space, x2 tilde, which is what basically has like a0, a1 all the way to ak minus 1. It has k vertices from p0 to pk minus 1, and it has therefore k copies of b that are labeled b0 to bk minus 1. Again, you may show by yourself that this space x2 tilde is homotopy equivalent to the wedge of k plus 1 is 1s, right? So we have k loops that are b, and then we have one big loop that is basically, well, a0 to a k minus 1, which I call it c here. So that's in total k plus 1 is 1s, all right? So you, again, try to prove this or convince yourself this is true. And in any case, out of this fact, we see that the fundamental group has k plus 1 generators, and it's a free group. Nice. And now let's see how, I mean, so this is like abstractly, right? Like we know out of this isomorphism, out of this homotopy equivalence, we know that there's this isomorphism of groups, but let's try to be extremely concrete. So how do I build the k plus 1 generators here? So you take, well, B0, this is obviously a loop in P0, then we can do the same as with before, A0, B1, and come back, A0, A1, B2, and come back, and so on. And out of this, you build k generators, basically one wrapping around each of the b's. And now you add one more generator, which is going around the a edges until you come back. And this I call C, but I could also equally call it just A0, A1, A2, all the way up to AK minus 1. All right. So this is a very explicit set of generators. And as we reasoned before, the B's go to the BI's go to B, and the and C goes to A to the K, and the A's go to A. So we get exactly the situation where this n ranges from 0 to k minus 1, as we said. All right, and again, this is similar to this situation. So now this group, what we've been able to do is to include the free group in k plus 1 generators into the free group with 2 generators, which is cool. Very good. We're almost there. I think I have a couple more examples. So as we saw in the case of S1, there were like essentially two types of covering spaces. There was S1 that was covering S1 by like wrapping k times. So these were like covering spaces that were not simply connected. And then there was one covering space that was R itself, which was simply connected, in fact, because it was contractible. For the case of X, we've seen two covering spaces that correspond to certain subgroups of pi1 of X, but they were certainly not simply connected, right? Because they corresponded to non-trivial subgroups. So what we're gonna do now in this picture, that hopefully will be more clear in a second, is produce covering space of X, which is simply connected. And in fact, we will show in a second that it is contractible. And I'm going to call this X tilde. All right, so the idea, right, is if I want to build sort of the largest covering space, is that I want to unwrap both A and B as much as I can. So how do you do this? So and let's recall our constraint. So since we are mapping to X eventually, we need that at every vertex there should be four edges, right? Because that's exactly what happens at the vertex of X, and they all have to be of this form. So one of them has to be an incoming A. Another one has to be an outgoing A. You must have an incoming B and an outgoing B. So out of this, how do we unwrap fully? So okay, let's start at P0, and let's say we move along A. Now we need to unwrap again. So then you must get a B, an A, and an incoming B. And now as we move to any of these edges, we will reach a new vertex, and again an unwrapping must happen. And you reach a new one, and unwrapping must happen. And you reach a new one, and so on. So that means that basically you get like a fractal shape. Every time you move by one of the vertices, you will get to a new vertex that has three new vertices that you can leave it from, essentially. So this will form this infinite shape where you can like just choose a path where like every time you select, oh, should I go using A, should I go using B, A inverse, or B inverse? And what does this tell you? So what is the logic here? What are these vertices? What do they represent? Well, they just represent words in pi1 of X, right? Because what does each vertex mean? So P0 will represent the empty word. This is just stay at your base point. And now I can choose, like, should I exit through B, through A, through B minus 1, or through A minus 1? And I leave along A. Okay, then I will call this vertex A. And now I choose again. Should I leave from B, from A, or B minus 1? And for instance, if I choose A again, then I will be at A squared, and I call this vertex in this manner. So basically, you just label each vertex by the word you had to follow to get there. Okay, and of course there's many words. For instance, I could say, oh, P0 is the same as I go through A and then I come back through A minus 1. But that's kind of like a silly choice, right? Because that's the word. I mean, it's an unreduced word. It's a word that is equivalent to just the empty word. So the precise claim is that vertices are labeled by the unique reduced word that leads you there. All right, so for instance, this is A and then B. So this vertex, I call it BA. This vertex, I call it B. This vertex, I call it A inverse, this I call B inverse, and so on. This I would call, for instance, V inverse A, and so on and so forth. All right. And this is really good because that what you should take from this is that if I have a path in X, well, not a path, right, but a class in pi1 of X, such a class is represented by an unreduced word. And now each element in pi1 represents a vertex here. And that tells me that every path, not every path, every loop in pi1 of X corresponds also to the path that has led me to that vertex. And that tells me additionally, and as we'll see in a second, that all the loops in X, they lift to paths that are never loops, because they tell you that you're going somewhere else, that you're going to a new vertex. I will try to make this more formal, but try to think about this claim. And to support this claim, let me now prove that this x tilde that is defined in this complicated way, this x tilde is contractible. And how do we show this? So let's do the following. So I'm going to define a sequence of subspaces of x tilde that I'm going to call them x tilde n. And what is x tilde n? They are like the vertices who are described by reduced words of length at most n. Okay, and not just the vertices, but the edges between them. So for instance, what's x0? x0 is just the vertices that are described by words of length 0, so just the empty word. So x0 is just p0. Now, what's x1? It's the vertices described by words of length 1 and the edges between them. So basically, it's described by the empty word, the word b, the word a, the word a inverse, the word b inverse, and the edges between them. So it's basically this cross. Similarly, x2 will be this cross. Then we will be together with this edge, 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 well, and the outgoing edges at these two vertices. Okay, and so on. And one of the first claims you can see, think about this, is that all of these xn's are compact because they are the union of finitely many edges. All right, this will be important in a second. All right, so you can also see that x tilde is the union of all the xn's, all x and tilde, so this is an infinite union. And now what we're going to do basically to show that x tilde is contractible is that we're going to show first that each x and tilde is contractible, and then we will sort of compose all these contractions. So how does this work? So indeed, so the claim is x and tilde deformation retracts to x n minus 1. And well, let me not show the proof, let me just remark. So let's say I have x1, which is this cross, and I have x0. So the claim in particular for n equal to 1 says that I can retract the cross to the point. And all you have to do is you take the four edges here, vertices, well, the corresponding edges, and you linearly contract them to p0. And that is the general idea, to construct the deformation retraction of fxn to xn minus 1. You're just going to retract like the last edges, essentially. A way to formalize this is the follows. So you say, well, let's take a vertex of described by a word of length exactly n. So this is, let's write it like this. So SW, so S is a symbol that is A, B, or well, A inverse, B inverse. And the rest of the word that has length n minus 1. And now what you do is you connect SW, the vertex of interest, to that has length n, to the vertex W that has length n minus 1, and you just retract the vertex between the two of them linearly. Okay, and this by definition will retract xn tilde to xn minus 1 tilde. All right, so each of these compact pieces is contractible, and now we must show that x tilde itself is contractible. And the idea, we've done it a few times for non-compact spaces. You do the following. So we want to basically compose all these deformation retractions. There's infinitely many of them, but you can do the following. So you say, look, in the last, well, okay, let me give names, right? So let's denote by ftn the deformation retraction of xn to xn. Oh, this should be, sorry, this should be from xn tilde to xn minus 1 tilde. My bad. I will correct this in the notes. So let me go on. So how do you define the deformation retraction of x tilde to x tilde itself just to x0? You say, well, in the last half of the time interval, I'm gonna assume that I've already retracted x tilde to x1 tilde, and then I apply the retraction from x1 to x0. Okay, then in the previous quarter of time, then I assume that I've already retracted x tilde to x2 tilde, and then what I do is I retract x2 tilde to x1 tilde, and so on. So in like progressively smaller and smaller intervals, you start retracting faster and faster. And the reason, I mean, and you might think that this is problematic, right? Because somehow as we approach 0, you are doing infinitely many deformation retractions, and that, sure, that looks problematic. But it is not, and the reason is that if you check what this map does over every compact set, well, in a compact set, this will only work. I mean, there will only be finitely many of these, right? Because every compact set is contained in some x and tilde, which is compact. All right, so you should think about this. It's important that you understand why, like how the topology of x tilde as a limit of x and tildes plays a role into why this is continuous. All right, and we are almost done. Yeah, okay, maybe let me make a last comment, which is that in this example, as we've said, I think I already made this comment, but let's do it again. So each loop is in x lifts to a path here, but never to a loop. And this is because loops in x correspond exactly to vertices, like into vertices that are copies of P0. Well, not copies, but yeah. All right. So let's move on to the last example, which is where like we just do like partial unwrapping, so we don't unwrap fully. You can try to work this out yourself. So here, as you can, I mean, the only thing you have to check here, right, is that this is some sort of graph in which we have k vertices, and at every vertex we have 4 edges, and it's incoming A, outgoing A, incoming B, outgoing B. So this tells you how you should be projecting, let's say, covering X with using this space. And you can check readily that the fundamental group of this space is the following. It's all the loops you may do are you do A first, and then you do B inverse, you do A twice, and then you do B inverse twice, you do A 3 times, and then B inverse thrice. And or you could just do like a whole loop of BK. And you should check that with these together, then doing A to the K, you can just build it out of combining these. And this is this should be clear because this space is homotopy equivalent to k plus 1 to a k plus 1 wedge of S1. So here I'm exactly giving you k plus 1 generators of the fundamental group. All right. So I suggest that you go to Hatcher page 58 and look at more examples there. And let me close with a final result, a small result, which says the following. We've been using it sort of all the time, all throughout this discussion. If we have X, a graph, so one-dimensional CW complex, then every covering space of X will also be a graph. And how do you do this? Well, you just take the vertices of X, and basically you impose that every pre-image of them in X tilde is also a vertex. And similarly, for every edge in X, you say that every pre-image of it in X tilde should be also an edge. And here you should do a bit of work to show that indeed, well, I mean, basically, all that you know is that since X tilde is a covering space of X, like there's always neighborhoods of points in X that look like that, such that their pre-image looks exactly like them. But you don't immediately know that the pre-image of an edge looks like an edge. So you should prove this. Yeah, you should prove this yourself. educational exercise that we will in fact sort of prove rigorously in the next video. All right, so that's it. You can expect the next video hopefully, I guess, tomorrow. And I'm hoping you'll have questions about this on our session, on our live session on Thursday. So yeah, take care and all the best.